Hey guys, as you all know, modern OpenGL is all about the programmable pipeline. This means that most of the rendering algorithm is implemented by the shaders. However, there are still a few bits and pieces of the graphics pipeline which are fixed function in nature. One example, which we usually don't think about, is the process of loading the vertex attributes into the vertex shader. This usually requires binding a VAO, enabling each vertex attribute, specifying things like the number and format of the attribute components, offset from the start of the vertex, and etc. All these operations are considered fixed function. Turns out that in recent years, various improvements to OpenGL created a possibility of loading the vertex attributes into the vertex shader in a programmable manner. We call this Programmable Vertex Pulling because the vertex is sort of pulled from inside the shader instead of having the attributes pushed into the shader by the system. The main thing here is that we don't need all the hassle of specifying the vertex layout in the C++ application code, and in some cases we don't even need a VAO. Instead, we bind the vertex buffer and optionally the index buffer directly to the vertex shader, using an OpenGL feature called Shader Storage Buffer Object, or SSBO. This feature became part of OpenGL in version 4.3, so make sure your driver supports it before you try it out. In the vertex shader, we use the GLSL internal variable GLVertexID in order to access the SSBO and pull the vertex attributes directly from it. I came across this technique as I was studying the 3D graphics rendering cookbook by Sergei Kosarevsky and Viktor Letipov for my Vulkan tutorial series, and I decided to implement it because they say that the technique is used extensively in this book. They also said that their implementation is actually based on a 2012 article by Daniel Rakos in the OpenGL Insights. Since I own pretty much all the OpenGL books in the world, I went ahead and read the original text. In his article, Daniel explains how to implement vertex pooling, describes the use cases and limitations, and most importantly, shares performance results from his experiments. In general, there are two levels to this technique. First, we have fully programmable vertex pooling, where both the index and the attributes are pulled by the vertex shader. Here, the GLVertexID variable is used to manually load the index from the index buffer, and then this index is used to load the vertex attributes from the vertex buffer. This is the case where the VAO can be dropped entirely from the setup. The second option, which he calls programmable attribute fetching, leaves the management of the index buffer to the VAO, so only the vertex attributes are pulled by the shader. The performance experiments that Daniel conducted on the 2012 GPUs show that programmable attribute fetching is pretty much on par with the fixed function operations. The fully programmable vertex pooling had a noticeable decline in performance, which is speculated to be the result of not being able to use the post-transform cache in this technique. But remember that what you're seeing here is not the overall performance of the application. This is just a focused measurement of loading the vertices. The performance of a graphics application is usually dominated by the complexity of the fragment shader, which is not affected by PVP. Anyway, what I'm saying is that you need to run your own experiments if you plan to use it. GPUs are constantly evolving, and there is a tendency to move away from stateful functionality, so it's possible that today there is no performance degradation from PVP. Okay, now let's talk a bit about the application of this feature. The most obvious feature of PVP is that it enables random access to the vertices in the vertex shader. The access pattern of the VS is usually very rigid. The system calls the vertex shader once for every index, according to the index order in the buffer. With PVP, we can use any index that we want and not just the current index. So, for example, we can access multiple vertices from the current, previous, and next primitive, which can make sense if you know the layout of the vertex buffer from a geometric point of view. Another possibility is to bind multiple SSBOs and access them in the VS in different frequencies. For example, we can have an SSBO with the per vertex data and an SSBO with the per primitive data. If you are familiar with instancing, then the two techniques may look the same. However, instancing has the same frequency for each buffer independently, whereas PVP allows you to change the frequency based on dynamic conditions. And finally, PVP enables loading attributes only if they are needed, again depending on dynamic conditions in the shader. This has the potential of reducing memory bandwidth, because in the fixed function method, all the attributes must be loaded to the VS. Okay, before we jump into the implementation, I'd like to say a big thank you to CyberReality, who recently joined the 3D Underground. If you too would like to support this channel, you can do that at patreon.com/OGLDEV or by joining the YouTube channel as a member. So let's start on the application side, and this class should be familiar to you if you've been following my tutorials on loading models using the SIMP library. In those videos, this class was called Basic Mesh. This is a newer version called Core Model, but it's basically the same thing. And right now we are in the populate buffers function, which takes a vector of vertices and populates the vertex and index buffers. So depending on the configuration flag use PVP, we can go the PVP way or the non-PVP way. And if we're not using PVP, this is basically the original code where we can populate the buffers using DSA, direct state access, or non-DSA for older versions of OpenGL. Now for PVP, we also check whether the OpenGL version is greater than or equal to 4.5. And the reason why we're checking for 4.5 and not 4.3 is that this function is also implemented for DSA. Okay, I don't have a non-DSA version of this function, so we need 4.5. So this function is right here below, and the first thing that you will notice is that it is very short, okay, compared to the older versions, the non-DSA and the DSA version, right? We don't have any of these functions like enable vertex array attrib or vertex array attrib format or binding, or these functions which are older like GL vertex attrib pointer. Okay, so this is basically the essence of PVP. Most of the stuff is in the vertex shader. So what we do need to do is to load the vertex and index buffers with data. And for that we use GL named buffer storage, which is the DSA version of GL buffer data. Okay? Now the handles for the vertex and index buffers have already been created using GL create buffers at an earlier stage. You can take a look at it later. So now that both buffers are populated, we call GL bind buffer base. And what this function does is that it binds the vertex buffer as an SSBO on the shader, on the vertex shader. So the first parameter is the GL shader storage buffer, which is the target. And then the second parameter is the binding point. So this is a running index. So we use the first one, 0. And if you have multiple SSBOs, you will simply call this function multiple times using the same target, different binding point, and the corresponding buffer. As you can see, this function actually supports 4 different targets, right? We have atomic counter buffer, transform feedback buffer, uniform buffer, a UBO, and the SSBO. So this is the one that we're using right now. Now in this example, we are not using the fully programmable vertex pulling. We use the other method, where the index buffer is managed by the VAO. So the vertex buffer is connected as an SSBO, and we will do that for both methods. But the index buffer is bound to the VAO using GL vertex array element buffer. So this is the standard function for binding an index buffer to the VAO when using DSA, direct state access. The VAO was also created at an earlier stage, at the same place where we created the buffers. And that's it in terms of the setup. So we can now go to the vertex shader. So first of all, the minimum version for this shader is 4.3. And this vertex shader supports both PVP and non-PVP, okay, the original version. And the way that we do that is using a pre-processing macro called PVP, which is defined here. And you can comment this in or out. And depending on whether it is defined or commented out, you will go to the PVP version or the original version here. So if you also want your shader to support both versions, you need to make sure that the vertex shader is synchronized with the application side. Okay, for example, with this flag. And right now I need to do this manually, but you can also do this programmatically by prepending this line to the shader before you compile it. Okay, so when you call GL shader source, you can prepend anything that you want to this string. And this can be any type of pre-processing macro. And the reason that we need to work like that is that unlike C, C++, GLSL doesn't support defining pre-processing macros on the command line of the compiler. So basically the only way is to modify the source directly, either manually or by hacking this string. So now we define the structure for the vertex, which is identical to what we have on the application side. Okay, so we have position, textual coordinates, normal, tangent, and bitangent. And notice that we're using an array of floats and not vec3 or vec4 or vec2. And the reason that we do that is because anything other than vec4 is padded to a vec4, and we don't want that. We need this to match what we have in our C++ vertex buffer. So in this case, we have an array of 3 floating points for most of the attributes, except 2 for the textual coordinates. Next, we define the SSBO, and we do that using the buffer keyword. So we have a buffer called vertices, and we have quite a few qualifiers here before the buffer, so let's take a look. First of all, we have the layout, and here we're using the keyword std430. And this keyword basically represents a set of rules for stuff like alignment and number of components and stuff like that. Not something that you need to worry about, just remember to use it. There used to be an older version called std140, but we need a newer version for PVP. Next, we define the binding point for the buffer, and we need to make sure that this matches the binding point on the application side when we call GL bind buffer base. Okay, if you don't define it, then the system will allocate it for you, and then you need to query for it, so it's easier to manage it yourself. Just make sure it matches the application. After the layout, we have the restrict keyword. And what this does is basically tell the system that this buffer is attached to a single binding point, because in theory, you can bind the same buffer to multiple binding points. So if you don't plan to do that, then it's always recommended to use restrict, and this will assist the compiler to optimize the code. The next keyword, read-only, is also about compiler optimizations. It tells the compiler that we're not going to write to this buffer, only read from it. So it's also recommended. Now inside the curly braces, we define the format of the buffer, which is an array of the vertex structure. As you can see, we don't need to set the size of the array. The system will calculate it for us based on the size of the vertex buffer. So now let's go to the main function. And I wanted to keep the code unchanged as much as possible. So what I did for PVP is to define local variables using the same names that we use for the vertex attributes in the non-PVP version. And for each attribute, we have a wrapper function which pulls the attribute from the SSBO. Okay, position, get position, text coord, get text coord, and all the rest. Each such function takes the index in the buffer where it needs to pull the attribute from. In this case, I'm using GL vertex ID, which is an internal GLSL system variable. And if this is a non-indexed draw, then this will be just a consecutive running index, 0, 1, 2, etc. If this is an index draw, then this will be the index from the index buffer for the current vertex, of course. The wrapper functions themselves are very simple. They basically return a vec3 or vec2, which is constructed using the corresponding element in the SSBO, right? So in vertices is the array in the SSBO, which is basically the vertex structure. And the vertex structure has 3 floating points for the position. So we take those 3 floating points and we initialize a vec3 and we return it. And same thing for all the other attributes. So now that the attributes are ready, we can continue with the rest of the shader as usual. And that is it for today. Of course, this video didn't cover all the information on PvP, so for more details, make sure you read the original article by Daniel Rakos. Let me know what you think about this technique and whether you already have some experience and can share performance results. Thank you for watching, and I will see you next time.